Hello students, we will be doing the potential energy formulation for deriving the elemental stiffness equations. In fact, this technique has already, all of you are already aware of this particular technique. You have already studied this technique in the course of vibrations, where you derived the energy of a single degree of freedom system and then differentiated the equation with respect to the number of unknowns available to you, and this gave you the required governing equation. The same approach is going to be followed here also. We are going to take a simple uh, bar. We are going to take a case of a bar element which is going to be loaded under all possible sort of loads. There are going to be point load also, there are going to be surface loads, and there are also going to be some um, volume load, body forces, that is. And then we are going to obtain the expression for energy for this loading, which is then going to be differentiated with respect to the unknowns to give you the required stiffness matrix. Now, this particular technique, this particular example is also going to serve as an example to illustrate the process which is going to be followed when you are dealing with the plane stress and plane strain cases, axisymmetric cases, and the three-dimensional cases. Now, what also is going to be new for you is that we are going to do the entire formulation with respect to the matrix approach also. We are going to do the entire formulation using the matrix approach also. And since matrix happen to be a new phenomenon, most of the students might be facing might not be aware of the matrix formulations, or they might be comparatively weaker corresponding to this particular exposure. So we will do the derivation both in the traditional method and using the matrix approach also. And the uh, entire derivations happen to be systematic in the sense that if you are able to understand how things are getting manipulated for a bar element obviously is the most simplest type of element in this particular case. So if you are able to understand the um, methodology which is going to be illustrated for the bar element, you can apply it for any sort of element, that is any sort of element which might exist in three-dimensional analysis or even in transient analysis. So this is where we start with the derivation. So for derivation, we are taking a case of a bar element. So a bar element uh, is represented by a single line. It has two nodes at its end because we are taking a linear element. Node number 1, node number 2. There is some force acting on node number 1 and there is some force acting at node number 2 also. And the positive direction of the bar element happens to be from node number 1 to node number 2. Apart from this, there happens to be a unknown displacement at node 1 and node 2. So this happens to be its degree of freedom. And then there are certain loadings on the element. We have point load at the two ends, which is acting at the two nodes given by F1x and F2x. Then there happens to be a surface traction or a surface force given by Tx, and there happens to be a body force also given by Xb. Now kindly notice that the derivation which we are going to make is going to be for the case when the traction or the body forces are acting throughout the element. What I want to say is that they are not restricted to a certain portion of the element, but they are acting throughout the entire element. So this gives us a constraint over here that if supposing there exists a bar and there is a surface load acting only on some particular portion of the bar, then then that particular portion of the bar is going to be considered as a single element, or maybe it is going to be broken down into a number of elements. But the thing is, there is no element which has loading restricted to a certain area in the element. The loading is going to be present in the entire domain of the element. So this is one of the constraints which we are going to follow for the development of the governing equation. Now starting with the derivation itself, the total potential energy is defined as the summation of the internal strain energy represented by U and the potential energy of the external forces denoted by ohm. So we have equation number 1. The total energy, potential energy is equal to summation of the internal and external energy. Now internal energy obviously is the energy which is going to be stored in the domain because of the straining present in it. Whensoever you apply forces on a particular body and the body happens to be elastic, the body is going to deform, that is it undergoes certain amount of straining in it, and correspondingly it is also going to store some energy corresponding to the which is better known as strain energy. Now this strain energy is obviously given as the expression number 2, which happens to be stress multiplied by strain integrated over the entire volume. And since we are developing this particular expression for a bar element, uh, you already know from the elementary theory of strength of materials that the bar element has only um, stresses and the strains acting along the x-axis. The remaining strains and the remaining stresses are basically uh, they are zero. So this is the only significant stress and strain which is present for the case of bar element. So this is how the internal energy is going to be evaluated. And if the area of cross section happens to be uniform, and if the area of cross section is uniform, then the stress and strain depends only upon x coordinate, for which we can simplify the expression number 2, which is now depicted in expression number 3, and correspondingly the volume integral reduces to a area integral. So we have terms such as area appearing in expression number 3, and corresponding integral reduces from volume integral to a one dimension integral. Now in this particular slide, we are simply going to substitute the expressions for displacement, which is given by expression number 1, in which case n happens to be the shape function or the interpolation function given by 1 minus x by L and x by L, and similarly the displacement is given by u1 and u2. This is equation number 3. Uh, since we are taking a line element, it has two nodes. Therefore, the both shape function and the displacement function happen to have only two elements in it. Shape function basically is a row vector, row matrix. The size is one row and two columns, where the displacement matrix happens to be of size two rows and one column. Obviously, these two can be multiplied together to find the value of displacement anywhere in the domain depending upon the value of x. And obviously, the multiplication of the two matrix is supposed to follow certain rules corresponding to matrix manipulation also. So those are the additional requirements on this matrix. Also notice the difference in which the two matrix is being illustrated. A column matrix such as equation number 3 appears in curly brackets, whereas the row matrix has square brackets at its end. So this is the notation we are going to use for for the matrices. Now, since strain is given by the differential of displacement with respect to x, and we already know the expression for displacement, we can differentiate equation number 1 to give the to give equation number 2, which represents basically strain, uh, where a matrix comes into picture given by minus 1 by L and 1 by L, which obviously is what is going to be obtained when the matrix N is going to be differentiated with respect to X. And this particular matrix has been illustrated with uh, B. So we are going to use throughout the derivation of the entire FEM, we are going to use matrix B, which basically is going to represent a matrix which has been obtained by differentiating the shape functions. The matrix B is going to represent a matrix obtained by differentiating the shape functions. This is given in equation number 3, and B itself is represented in equation number 4. Now, once strain is known, we can obviously multiply it by the elasticity matrix to get the corresponding value of stress, which is expressed in equation number 5. Now, the thing is that in uh, the analysis of a bar, we have only one strain available and only one stress available. So, therefore, the D matrix basically reduces to a matrix of size 1 by 1, and which is basically going to be the elasticity. But for other cases, such as plane strain, plane stress, or three-dimensional, let's talk about the three-dimensional case. In three-dimensional analysis, there are going to be 6 strains, there are going to be 6 stresses also, and the stress and the strain are going to be related with respect to each other by an equation of type which is represented in equation number 5. So correspondingly, the D matrix is going to be of size 6 by 6. Obviously, D matrix itself is going to contain terms of elasticity. There might be a there is going to be a bulk modulus also, and there is going to be a Poisson ratio also. And for some isotropic homogeneous material, the D matrix is going to be a symmetric matrix also. But for some other type of materials, the D matrix might not be symmetrical, or it might not be fully populated and things like that. So depending upon the material which you are modeling, the D matrix is going to be taken up corresponding to the material properties. Now, once we substitute equation number 2 in equation number 5, we get a relationship between stress and displacement given in equation number 6. This is obtained simply by replacing the expression for strain in equation number 5. So we have obtained equation number 1, which represents a relationship between strain and displacement. Equation number 2, which represents stress and strain, and equation number 3, which represents the deformation. And when you substitute all these equations uh, in the energy equation, we get equation number 4, in which the first term on the right, which is a product of stress into strain, represents internal straining. Now, the next two terms, that is term number 2 and term number 3, represents the amount of energy because of point load. Here we apply the load acting at the point corresponding and with the displacement existing at that particular point. So the product of these two simply gives us energy at that particular point. So the terms second and the third term correspond to the energy corresponding to the point forces. Now the fourth term, that is U multiplied by T ds, represents the energy because of the surface loading, where U represents the deformation and T represents the surface load. And since we are talking about the surface load, the corresponding integration is over the entire surface. And the last term on the right represents the volume energy. Here we represents the U. Here we multiply the deformation with respect to the loading, volume loading, and there is a corresponding volume integral. Now, specifically when we talk about the bar element, the U which appears in surface loading and the U which appears in the volume loading, these two basically are they are the same. But when you are talking about 3D elements, the expression for displacement in these two expressions, that is the surface energy and the volume energy, these two are going to be different, simply because for finding the surface energy you require surface displacements, and for finding the volume energy you require volume displacement. So obviously, since surface displacement is going to be represented, surface displacement is going to be represented by some other polynomial, and the volume displacement is going to be represented by some other polynomial. Therefore, they are going to be two different polynomials. But in this particular case of bar element, both these two displacement polynomial happen to be same. So in this case, that is expression number 4 presently on display. The U appearing in both these terms, that is the surface energy and the volume energy, they basically are the same expressions. And in the next expression, we are simply going to substitute expressions number 1, 2 and 3 in equation number 4 to get the energy basically in a matrix form. So this might require some explanation. So we are just explaining equation number 5 term by term. The first term is the energy representing the strain energy, and since alpha x and sigma x, that is the stress and the strain matrix, both happen to be a column vector. Therefore, the transpose of the first one is supposed to be taken. The first matrix is supposed to be transposed, and then it is supposed to be multiplied by the second matrix. So this is how matrix manipulation is going to come into picture. Therefore, the sigma x has a T superscript written on top of it, which basically means that we are taking the transpose of the stress matrix. And similarly, coming to the second term, where we are evaluating the energy because of point forces, we are taking the transpose of the first matrix, that is transpose T of the displacement matrix. Now, similar transposes have been taken for finding the energy because of surface and the volume loads. And in the next slide, we are simply going to substitute the expressions for stress, strain to get this expression. Uh, so, in when you substitute equation number 1, 2 and 3 in equation number 4, we get equation number 5. Now this also might require a certain amount of explanation. So we are explaining this particular expression term by term. We start with the first expression on the right of the equality sign, where basically we are multiplying the transpose of stress with respect to strain. Now stress obviously is given by expression number 3, which has a multiplication of 3 matrices represented by D, B and small d. So when you take the transpose of stress matrix, another property of matrix manipulation comes into picture. The property is that you reverse the order of matrix multiplication. You reverse the order of matrix multiplication and you take the transpose also of all the matrices which are going to be involved. Now this gives us first 3 terms of the um, strain energy, but the other 2 terms, that is capital B and D, this represents the strain energy, strain term. So this is how the energy term is being obtained. Now the second term on the right hand side, that is the energy of the point forces. This probably does not require any explanation. And the third and the fourth term on the right, uh, this involves the matrix manipulation, which was just illustrated with the help of the first expression on the right. So this is how the energy is going to be represented in terms of individual matrices. So we start with the energy expression once again. We have 4 energy on display: strain energy, also known as the internal energy, then energy because of the point force, energy because of surface forces, and energy because of the volume loading. And if we just notice the highlighted area, we are multiplying the transpose of D matrix with a force. Obviously, when these 2 matrices are being multiplied together, you get the corresponding energy. Now the thing is that the transpose of D matrix appears in the third and the fourth term also. The transpose of the D matrix appears in the third and the fourth term also. So which basically means that this term which is highlighted just now and this term which is highlighted just now also represents forces. So we can club all these 3 forces together because they are forces acting in the equation. We can club the 3 types of forces which are on display to give you a single expression given by equation number 1, where the P matrix now represents the summation of all the type of forces acting on the body. We have F, which represents point forces. We have Fs representing surface forces, and we have Fb representing the volume forces. And the expressions of surface forces and volume forces are given by expressions in equation number 3 and equation number 4. Now, discussing something about equation number 3, and a similar discussion is going to be applicable for equation number 4 also. Equation number 3 represents that if there is a surface loading on an element represented by capital T, then it can simply be manipulated by this shape function and integrated over the surface to give Fs, which means that equation number 3 can be used to transform or to get The to convert the surface load into equivalent point forces acting at the two nodes. Equation number 3 can be used to transfer the surface load into equivalent loads acting at the two nodes of the element. Similarly, equation number 4 can be used to transform the body forces, that is a force such as simple as a gravitational or magnetic forces. Equation number 4 can be used to transfer the body forces into equivalent forces acting on the nodes of the element. So this is how equation number 3 and equation number 4 are going to be of immense advantage to us. And obviously all the three forces acting on the element, that is the point forces, body forces and the surface forces, collectively they are represented by P, capital P, given in equation number 2. Now these two forces, that is Fs and Fb, are called consistent forces because they are based on the same shape functions used to calculate the element stiffness matrix. These two forces, Fs and Fv, are also known as consistent because they are based on the same shape functions which is used to calculate the elemental stiffness matrix. Obviously, this means that there happens to be certain category of forces which is non-consistent, which basically is going to use a shape function which is different from the shape function used for evaluating the stiffness of the matrix. And the other thing to be noticed is the loads calculated are also statically equivalent to the original loading. This means that both Fs and Fb and the original loads yield the same resultant forces and same moment about any arbitrary chosen point. So they happen to be statically equivalent also. Now just uh, another point which just came into my conscious, that you have already studied the cases of bar which has been subjected to uniformly distributed load over the entire bar, and obviously you can find out the uh, reactions of the two endpoints. If you take a bar which is, let's suppose, simply supported at the two endpoints and the bar is subjected to uniformly loading, so you can easily find out, depending depending upon the knowledge which you have already acquired in your BTech courses, you can easily find out the reactions at the two endpoints. Now, uh, these two forces which you can obtain from your elementary SOM knowledge and the forces which you can evaluate using the expressions developed in the present FEM course. Basically, they are going to be same. This is another thing which has to be kept in mind. Now, this basically means that we have evaluated the energy of the system, and as you have already studied in your elementary courses of vibrations, that once the energy of the system has been obtained, you basically differentiate it with respect to the unknowns to give you the required governing equations. So the same process is going to be repeated here also, but just for the explanation purpose, we are going to we are going to expand the energy terms just for the understanding purpose. We are actually going to do the entire derivation through two techniques. We are going to expand the energy expressed in matrix into a algebraic equation, and then we are going to differentiate it so that you develop a better understanding. So expanding the internal energy first, which in a matrix form is given in equation number 1. Obviously, um, you know the various representations. If you substitute the matrix for D, B, capital D, etc., what you get is equation number 2, which can be multiplied together to give the equation number 3, which obviously is a quadratic equation in terms of U1 and U2. U1 and U2 are the two nodal displacements which are basically unknown. So the internal energy is given by uh, that is equation number 3. Now similarly, the forces can also be expanded, that is in equation number 1, and when you add equation number 0 and equation number 1, you get the entire expression for the energy term, which is given in equation number 2. This obviously has two unknowns given by U1 and U2. So when you differentiate when you differentiate with respect to the first unknown, that is U1, you get equation number 1, and when you differentiate it with respect to U2, you get equation number 2, and obviously these two equations can be clubbed together to in a matrix form. This is going to give you equation number 3. So this is the required governing equation, which obviously has been obtained using the matrix approach, and equation number 3 basically is the same equation which was obtained using the direct stiffness formulation in the earlier classes. But in the present form, we basically are obtaining the equations using the matrix approach. Now here is basically a shortcut. Supposing you can represent the energy of the system in a matrix form given by equation number 0, then if you simply differentiate it with respect to the D vector, D obviously happens to be the degree of freedom or the unknowns, what you get is equation number 1. Where the three terms, that is B transpose, D transpose and B, are being clubbed together to give you the stiffness of the matrix. And the other thing is that which is going to be apparent when you look at equation number 3. If you talk about isometric homogeneous material, D happens to be a symmetrical matrix. D is a symmetrical matrix which obviously represents the properties of the material, but for an isotropic homogeneous material, D is going to be a symmetric matrix. And when a symmetric matrix is multiplied by a matrix B, is post multiplied by a matrix B and pre-multiplied by transpose of matrix B. Okay? The thing is, when you multiply a symmetric matrix by a matrix and pre-multiply it by the transpose of the same matrix, the result is going to be again a symmetric matrix. So the stiffness K matrix, which is being written in equation number 3, basically represents a symmetric matrix also. It is going to be a square matrix also, but apart from this, it is going to be a symmetric matrix also. So this is where we end this particular topic, and you can raise any queries. You can convey them to me with respect to the WhatsApp or email, whatsoever is convenient to you.